So what I'm going to talk about is more like applications of some of the observations of yesterday. So as I said, I'm interested in subadditivity. And we know, for instance, that entropy is subadditive in the sense that h of x1, x2 is less than or equal to entropy of x1 plus entropy of x2. And as I said, I'm interested in whether other functions are subadditive. In particular, there are many functions where I'm interested to show subadditivity, but that's not what I'm going to talk today. But I'm going to show you at least one function which you may not have seen, which is subadditive, which might appear surprising to you. But I'm going to use the subadditivity or proof of subadditivity to actually show something which had a very, very complicated proof. And this technique I'm going to develop also help me solve something that is open. So it's both useful and it's something. So let me start with the. Okay, so the setting is you have a sender x, and think of him using two channels. One says W1 of y given x. There's a noisy version y, and it's also there's another noisy version, say W2 of z given x, which is z. So think of it as two receivers. This person hears a noisy version, and this person hears a different noisy version. Now what do we know? We know, for instance, that if I fix these channels, so think of these as channels, then I know that, say, Ixy is concave in P of x. This is an elementary result. I mean, this is easy. Now what I'm going to do is I'm going to take Ixy and Ixm. What I'm going to do is I'm going to take, say, for any parameter lambda that's bigger than 1, I'm going to take Ixy minus lambda Ixz. I'm going to take this function. So think of this as a function of, let me call this some, say, f of the input distribution x is defined as this quantity. So if say, for instance, x is binary, then you can think of as a function something like this, which will be positive or negative. Then I'm going to take, so let me call capital F of x to be the upper concave envelope, which is the smallest concave function that dominates it, of f of x. Okay, so this is my function. So it's the upper concave envelope of the difference of mutual informations. Upper concave envelope is the smallest concave function that sits above it. So I'm going to make this difference concave by just taking the best mixture. Does that make sense? It's just a function. I'm going to take this Ixz, and I'm going to take the upper concave envelope. So it's a function of input distribution, right? Because channels are fixed, so these are functions of input distributions. So I can plot this as a function of input distribution. On that simplex, I take the upper concave envelope. That's this function. Okay. So the claim is that first the claim is that it depends on lambda. I'm fixing lambda. Lambda is some constant bigger than 1, and the claim it depends on. Okay. So the hidden parameters are lambda, W1, and W2. That's the hidden parameter. So it depends on lambda, it depends on channel, and depends on the two channels. So the claim is that f lambda, in particular, if I take W1, say one tensor W1 2 and W2 1 tensor, that means I take independent channels of x1 x2, some joint law, this is less than or equal to f lambda. So this is subadditive, W1 1 W2 1 of x marginal x1 plus f lambda W2 1 W1 2, I mean the second 2 of x2. So this function is subadditive. Note that this is not subadditive in general, but if I take the concave envelope, that is subadditive. And this particular property is really if you look at the heart of a lot of converses in multi-use domain theory, this is really the heart of many of the converses. Okay, so this, the subadditivity of this is really at the heart of many of the converses, and I can trace whatever argument I am giving today to Janosch's paper with, Janosch and Cesar, that whole bunch of, I'm going to trace a proof. So this is subadditive, and so I will show the subadditivity. It's very simple, but there's also another question which people. So this is the first result I will show. It's a very simple result. It's not hard at all to show. And the second result I'm going to show is that if I want to suppose, okay, now let's look at the following thing, and I will tell you why it's interesting. So this is related to. So if I take a particular channel model, say some y, it's an Rn. So y is equal to some Ax plus z. Z is a Gaussian noise. This is a Gaussian noise, and say, okay, maybe we call it y1, and the other receiver y2 is equal to some bx plus z2. This is also Gaussian, independent of everything else. And now I can ask where is this maximum for which input distribution subject to some. So I'm going to ask. I want to find. Okay, I want to find argmax, say, of subject to this condition. I have a covariance condition on the input. This is like power constraints. I want to find the argmax of f of x. Okay. So, and the theorem I'm going to show is that you have to look. The argmax is a Gaussian. So maximizer is a Gaussian, not necessarily with covariance k, but with some covariance less than or equal to k. I don't know what the covariance is. The technique I'm going to show, I can also show in general. The technique I'm going to show is essentially comes from this proof that this is a Gaussian. And the second thing is that, this result was known. Okay, this technique can be used in other places, but this particular result was known. And the way it was known was like probably a sequence of papers, multiple papers. So if you want to put all the papers, if you want to put a full proof together, at least 100 pages. And it involves entropy power inequality, which involves path variations, a lot of the ideas that Villani talked about, Gaussian perturbation and so on, to get this, because it's rather a nasty function. But I'll show you how to get. I can give a complete proof of this. Subject to one simple result, just from this subadditivity. So that's the first result I want to talk about today. First pair of results, and if I have time, I'll talk about something else. But let's see. So I want to first show that this function is subadditive, and I want to use that to conclude that the maximizer is a Gaussian. Yeah, so essentially this proof essentially works for anything that's subadditive. So when you have a Gaussian thing, so I have a more complicated function. So this is actually let me say a mechanism where when you have proof subadditivity, how to convert that to a proof that something is Gaussian. And the traditional way was using entropy power inequality and things like that, where we don't need to use any of this. So you can just look from the proof of. So you will see some of the ideas. Okay, this is one of the. The old approach was kind of using some of the flows which Villani talked about. Here I'm going to use a different convolution approach. It's very straightforward, and which will get you the same result.
Can you explain please what is so special in this function distribution formation between x and y minus lambda and distribution?
Oh, why is this come about? Oh. Okay, Okay, this comes up as the answer to a lot of questions. So let me tell you one of the questions which may be of interest to you. It's a question that Janosch said at the end of yesterday's post last yesterday's lecture. So images after 2 channels. So if I have 2 channels and look at the images of the x and yn and zn, and look at the single letter expression of that, or degrade message sets, or a bunch of things, you will see that this is the thing that comes about. And if you had we had the u last time, and if we want to find the optimal u, that's like the question here. So which is the best auxiliary or which is the best distribution, that gives you the set, the cluster in the typical set, which is important, and that's kind of these things. Okay, so this just come about in a lot of, that's why people studied this before, and comes about very naturally in a bunch of settings. And this lambda, the other thing is, this subadditivity holds for any lambda bigger than 1. It trivially holds also for lambda less than 0. But between 0 and 1, there can be counterexamples. So there is, I mean, if lambda is less than 0, it's just sum of mutual information, then their subadditive is very simple. It's also true for bigger than 1, but if you take something that's between 0 and 1, it may not hold. I mean, there are examples where it doesn't hold.
For negative number, is it trivial?
Trivial, it's trivial, because it's just sum of mutual. I just want to say that there is a, it holds at both the extremes, but in the middle there is some range where it doesn't hold. Okay, sometimes these are sometimes, I mean, interesting, but okay. So I will use. So you will see in the proof. So I'm going to just look at lambda bigger than 1. Okay. So how does this proof go? So another facet of this proof. So you may not see it in this proof, but if I look at traditionally how kind of these arguments were written, they are not written in this language. But if I look at some of the arguments, it's really, again, it reminds me of what Henri was mentioning. This like he had this kind of, I mean, disjoinous problem where you had this I, and you gave this to one person and gave this to some other person, right? You had, this is like the past and future, and this is the standard thing which we use in information theory. So this dates back, I don't know who, this is what, one of you, Janusz or Cizar's work. I mean, we call it Cizar's identity, but here it's very simple. You don't even need to see that, but you will see some aspect of it. Okay, so let's see how we prove this. So how do I prove that? So what am I doing? I am finding the concave envelope is the best convex combination. Okay, in a simplex is the best convex combination. So we know by Theodori's theorem, you have to look at the size, dimension, number of points, you get a convex combination. So let's say that the f of x1, x2 of a joint distribution was obtained by some convex combination. So it's some convex combination. I'm going to denote the convex combination by as some u. So it's I x1, x2, y1, y2 minus lambda I x1, x2, condition on u minus, because this is just convexification. So this is the best. So this is somehow the optimal convex combination. I'm just going to call it u. Now what am I going to do? I'm going to apply chain rule. That's all I'm going to use. And we know that, what do we know? We know that the input x1 produces the output pair y1 and z1, and the input x2, they could be correlated. I don't care about the correlation, but the output y2 and z2 just depends on input x2. So this is kind of the relationship between the random variables. So think of the pair generated from this, and think of this pair generated by this. This could be arbitrarily correlated. But there is a Markov chain. So all of these to x1 to y1, z1 is Markov, and so on. So I'm going to use this. I'm going to write this. This is just chain rule. What do I get? I get this equal to I. Okay, maybe I'll do one term slowly. I x1, x2, y1 given u plus I x1, x2, y2 given u, y1. That's the first term. I'm just breaking this up using chain rule. I'm going to break up the second term. Minus lambda I x1, x2. I can break it up. I'm going to break it up differently. Z2 given u. I mean, so it's a minus I x1, x2, z1 given u, z2. So that's possible. And now because y1 just depends on x1, I could drop this out. This goes away. y2 depends on x2, only x1 is a Markov chain, so this goes away, and this goes away. So now I could write this as, now I know I could introduce z2 here, so I can actually write this as I x1 y1 given u z2 plus I z2 y1 given u. So z2 will go up, but it's behind x1, so that's this exactly this term, plus I x2 y2 given u y1 minus lambda. I'm going to do the same thing here. I'm going to do I x2 z2 given u and y1, and then I'm going to put plus, so minus lambda I y1 z2 given u minus lambda, I'm just going to copy this, the blue term down, minus lambda I, oh this is minus lambda here, minus lambda I x1 z1 given u z2. So all I did is just introduce this term, but now you can see something nice. Okay, first of all look at this term and look at this term. So this is, so think of this as a new convex combination. So this convex combination is clearly less than the best convex combination. So this is less than or equal to the best convex combination. So that's my f of x1, because this is one particular convex combination is less than the best one. And similarly look at this, and this is less than the best convex combination, plus f of x2, and these two terms are same, so I get plus 1 minus lambda I y1 z2 given u. So if lambda is bigger than 1, this is negative, so this inequality holds. Okay, so here is where I use lambda is bigger than 1, so this becomes negative, and so that's the subadditivity of the concave envelope. So I needed the concave envelope, I used it, and I got subadditivity. So this is subadditive. Okay, so now is this clear? It's just algebra. So I started.
Maybe I just missed. Where did you use the fact that you are
Oh, because I chose that there is the optimizing u, and then I said that, oh, I get a new u, but the new u is obviously at least it cannot be better than the best u, so it's less than the concave envelope. Without the concave envelope, I cannot go from here to here. So and then I use both the concave envelope and lambda is bigger than 1. Okay, so this gives you, so this is subadditive, it's okay, and this is a, okay, now let's assume that we have a Gaussian thing. We have a Gaussian channel, and I want to show that the optimizer is Gaussian, the maximizer is Gaussian. So we don't know, but so what I'm going to do is I'm going to use this proof to tell me some property of the maximizer, and from that conclude that it must have been Gaussian. Okay, what can I do? So let's say that, okay, so what do I know? Let's say that let's take this. I want to keep this because I want to look at this expression at the end. So let's say that the optimizing distribution was some x star, and the maximizer was some value v was equal to some ix star y1 given u star, that's the best convex combination, minus ix star lambda y2 given u. Okay, that's my best, that's a maximum value, and this is the maximizing distribution. So what am I going to do? I'm going to take two independent copies of the maximizing distribution. So I'm going to take x1, x2. I'm going to take u1, u2 to be completely independent, and this pair is independent of this, and they are IID u star x star. Okay. And so now if I evaluate this expression with these, so let me write it here. So if I evaluate I x1, x2, y1, y2 given u, which is really u1, u2, minus lambda I x1, x2, y1, y z1, z. I should be careful here. So it's y11, y12, y21, y22, 2. There are two channels here. Given u, when they're independent, this just separates out. So this is just 2v. So we know that because they're independent, it's 2v. So that's the it's twice the maximum value because everything is independent. Both the components are independent. I mean, x1 is independent of x2. It's just, is it clear?
Did you write u1, u2?
Yes, I wrote, okay, u1, u2, yes. So this is just, everything is independent. So things separate out, that's 2v. Okay. Now what is the key point? The key point is that I'm going to replace, I'm going to call, say, x plus to be equal to x1 plus x2 by root 2. So I'm going to rotate the vector. I'm going to draw x minus to be x1 minus x2 by root 2. I'm going to use the fact that this channel is a linear channel. So what do I get? I get y plus is equal to a x plus. So I'm going to call this plus z plus, the same operation, and y minus is equal to, say, so I'm going to do the same operation. So the key property is that the Gaussians, if I do a rotation by 90 degrees, the Gaussians remain independent. So I could replace this join law by this join law because everything remains same. The channel is preserved. The channel is still the same channel because it is so instead of this input distribution, this pair, I could have given this pair. And because mutual information doesn't change on bijective transformations, so you could just do the same thing. So value is not. So that's all I'm using. I'm using mutual information preserved to say that this must be equal to Ix plus x minus y plus, y1 plus, say, y1 minus given u1, u2 minus lambda times this. Now what am I going to do? I'm going to apply this trick to y plus and y minus. So then I get to here, but I know that if x satisfies covariance constraint, this also satisfies covariance constraint k, this also satisfies covariance constraint k. So clearly this must be less than or equal to v, this must be less than or equal to v, but I started with 2v. So in particular I can conclude that this must be v, this must be v, and that this must be 0 because this is negative. So which means that I conclude, I get that this must be independent. So so there's a very elementary fact that if I have two random variables, if x and y are independent and x plus y and x minus y are independent, then they have to be Gaussians. Okay, this is a very elementary fact, and so the distribution is Gaussian. That's all I use. So I just use a tensorization proof to conclude that this must be independent, and then I know that if these are independent and these are independent, then there's Gaussians. So that's the only thing I use. So I use convolution. I use the fact that if you're the maximum and you do this transformation, you cannot improve, so you must be at the Gaussians. So that's kind of the idea, and so no entropy power inequality, no flow. It's all discrete stuff, except at the end I use some Gaussianity. I use linearity also here to show, and this solves all the things we could prove using EPI, and it also solves something we couldn't solve using EPI. So this is the trick. Okay. No, if x and y are independent, and x plus y and x minus y independent, they must be Gaussian.
And there are
no other distributions. Okay. If you want a proof, I can give you a proof. It's not hard. But or I can tell you how you prove it. Oh, No. So this is, I don't know, it's not a very, okay, this is, okay, there are many versions of it. So what is the, I mean, this is first put in 1940s, and then I would call it the skip. I mean, there are many stronger versions of it, but this particular thing, okay, I can skip it. Yeah. So I'll tell you in one line. If you use characteristic function, it's just, I give it an exercise in probability theory. So the only solution of the functional recursion is, okay, you need to give a hint, but that's it. If you use characteristic function, it's one line, shows that the only solution of the functional equation is e power minus ct square. And that's just a high school kind of Olympiad kind of problem where you just solve the equation and you see that there's only one solution. So, but yeah, that's the kind of way people prove it. So you have nothing, you assume nothing more than characteristic function, and then you observe it. I can talk to you offline, but it's a very simple fact. I didn't even write, I mean, it's a very, but it's a well known thing. For in statistics, it's well known. So I think this particular thing, I call it Darmo characterization. So if you look at this, but these are much more fancier than just the vanilla version I told you. But so it's a characterization of Gaussians, of multivariate Gaussians and things like that. But this could be inferred even very simply. So okay, so that's kind of the idea, and this is a useful property, and you can use it to show. We use it to show some vector Gaussian with common message we couldn't show. So that's the first thing I want to talk about. Okay. So the second, okay, is that okay? Or that's kind of, so okay. So you see that there are this function. Okay, I have, so this tensorizes. Few more things before I change topic. So there are other functions quite similar to this, which I would like to show subadditivity, which I can't show subadditivity. And this proof, so let me also comment on this proof. So if you see the way I broke this up, I broke z2 here and y1 here. So this is exactly what I'm saying. So you break one to the previous part and the other in the future part. This is the past and the future you see coming up here. Okay, and this is really, I mean, if you look at what you do, it's just exactly this. But here you don't have to do the César sum lemma, which is like I minus 1 zi given. You don't have to do that because it's just two variables. So it's I y1 z2. So it's much simpler in some sense to understand, and that's exactly what happens. So, okay, so for those, okay, let me just write for those. There's a, so you know, if you look at the old books, if you look at the n-letter versions, it's essentially, this is kind of the place where they use this inequality, that this inequality holds. So I z okay. Let me see if I'm getting this correct. Yi minus 1. So this equality was used in several cases, but for any equal to 1 it's trivial, and that's exactly what we use. So this is called César sum identity. I think we call it for some reason, but I don't know if the right, it is stuck. You know.
It came up in a paper, I don't remember what the paper's title was, but it's a paper of mine with Cotton and it deals, among other things, with what we call the zigzag source network.
But that was in 77 or something, right? Or yeah, around that time. But this came up, yeah, few people. I mean, this is just very simple. You expand it two different ways, and it's very simple. But this identity was used in many of the converses. But if you look at this, it's exactly the motivation for this proof is exactly that. Okay, so yeah, but the name, unfortunately, in the literature is César sum identity for some reason. But okay, so that is the. So that's this, and yeah. So okay, the next thing I want to talk about is completely a different topic, but before one more thing. Let me answer your question in a different way. Why is this function interesting? One more reason why it's interesting. if I put z equal to x, a trivial channel, this is S star. This is the function that comes up in the hypercontractivity S star. That's another reason. So it's in a generalization, but also it follows from Janos's because that's for one receiver. So it's 2 receivers, a generalization of that for 2 receivers. Oh, S star would be the smallest lambda such that this function is equal to the underlying function. So S star was defined as the first lambda where this becomes equal to or 1 over that. I mean, so you vary over lambda and look at the first point where it hits the function. That's S star. So yes, so there is a parameter in lambda, but that's a characteristic of S star, and this comes up also there. So in some sense, this is a generalization of hypercontractivity for 2 different reasons. Okay, so now I can go to a second application, which is a completely different setting, and my results are much weaker than here, but I think it's interesting so it's very different. So I'm going to completely go away from here. And this is actually more tuned to CS audience because I'm going to talk about Boolean functions, and I'm going to talk about some things about Boolean functions. So I can erase everything. So okay, so this is what I'm going to talk about. Is most of it is not published or not even submitted. It's just things which I know, which some other people also have communicated with. So, okay, so there is this conjecture on Boolean function, which says that for any Boolean function on the hypercube, f of n. So you xn, you pass it IID and produce a yn. So noise operator. There are many versions of it now. That means every xi is passed through a BSC with crossover 1 minus rho over 2. You operate yi, and the conjecture is that I of f of xn, yn is less than or equal to 1 minus, say the binary entropy of 1 minus rho over 2. And this is called the Kumar-Kumar-Couttet conjecture, but it's really a conjecture of Gautam Kumar, who told me even long before Couttet got into this problem. So, but they did something. It was published with Couttet. So I'm going to talk something about what I know about this conjecture, and I'm going to talk stronger forms of this conjecture. So this conjecture is open, and there have been several results, partial results on some various directions. But what I want to talk about first of all is a different. I'm going to do a parallel with a different conjecture. So in fact, what I'm going to present it. So one way to write. So there is this notion of phi entropy, which some people have seen. So phi entropy of a random variable is, so phi is a convex function. And the phi entropy of a random variable is expected value of phi of x minus phi of expected value of x. So that's the phi entropy. And depending if phi has some nice properties, this has tensorization and so on. So I forget exactly, but I think if phi is convex and if 1 over phi double prime is strictly concave, then there is a tensorization of phi entropy and so on. So this is the phi entropy. So now let's take phi of x to be the Jensen-Shannon divergence. I'll explain this if you haven't seen before. It's a Jensen-Shannon divergence between 2 distributions. So x, it's a binary distribution xn 1 minus x with 1 minus x and x. So that's what is Jensen-Shannon divergence between 2 distributions p and q. It is just half of the Kullback-Leibler divergence between p and p plus q over 2. plus half dq p plus q over 2. So I can, so that's the density and divergence. So this conjecture I can just rephrase, as the, so look at the phi, I mean phi entropy, so the phi is Jensen-Shannon phi entropy of, so what is my random variable? My random variable, so think of the random variable z to be the expected value of my Boolean function. So now I think of the Boolean function, as mapping to plus minus 1, plus 1 minus 1. So think of the expected value of Boolean function conditioned on yn, the received symbol. So that's my random variable z. So this essentially says that if I look at, so zf less than or equal to phi Jensen-Shannon of z dictator. So that's exactly, so which means that the function that maximizes this Jensen-Shannon divergence of the function is the dictator function. That's just a rephrasing of the, I've done anything because this is really for this particular function, phi entropy is just 1 minus entropy of the binary entropy of x. So that's just the statement, restatement. Why am I restating like this? So now I can put a different distance between measures. So I'm going to replace this Jensen-Shannon by the Hellinger squared. What is the Hellinger squared between p and q? Is essentially summation over I square root pi minus square root qi the whole square. So my new function, say phi hat of x is going to be the Hellinger squared, again between x and 1 minus x and x, and x and 1 minus x. So this is, and now I can ask, so I can guess whether phi Hellinger squared of zf is less than or equal to phi Hellinger squared of z dictator. Okay, so this could be a conjecture. Okay, and this I think is a so we are putting as a conjecture. So we can replace Jensen-Shannon by Hellinger. And why is this interesting? So I'm going to advocate that this may be interesting. So there are two reasons why this is interesting. This will imply this. So this is actually a stronger conjecture than the Jensen-Shannon than this conjecture. So if I show this conjecture, I will prove this conjecture in general. That's the first reason why this may be interesting. That this is a way to show. And now we don't have logs because this is really h of x. So phi hat of x is just 1 minus square root 1 minus x square. So depending on whether you like logs or square roots, this may be an easier function to work with. So if I want to put this, so this is really, I mean if I want to put this, so I want to say if I look at root of 1 minus expected value of f the whole square minus expected value of square root of 1 minus t rho f, this is a CS notation, t rho f squared, I want to show that this is less than or equal to 1 minus square root 1 minus rho squared. That's, I'm just writing this in the same way as you write this. That's exactly, so t rho f is just expected value f given y. So this is the conjecture, and you can show that this implies this, and the way you show that this implies this is if I look at the binary entropy of 1 minus square root 1 minus x square over 2, this function is convex and increasing. And you can use, so this is like Mrs. Gerber's lemma, or it's a different function inside, and we use this to show that this implies this. Okay, it's not hard, it's just a few lines of exercise to show that this implies this. Okay, so that's one reason. Let's look at a different reason why this might be a more nicer conjecture than this conjecture. If I let rho tend to 1, this conjecture reduces to, so for balanced functions, for instance, for balanced functions, it reduces to the expected value of the sensitivity of x is bigger than or equal to 1, which we know is a true fact. This is Harper's isoperimetric inequality. Now here, for the new conjecture, if I take rho goes to 1, again for balanced function, what you will, if this is true, then what it shows is that square root of sensitivity is bigger than or equal to 1, and this is not known, and the best known lower bound for this is square root 2 over pi. This is by Bobkov. So, and for majority square root pi over 2. So this is, even in this limit, this gives you something new if it's true, and there's no reason to doubt why this is false. So this gives you, and this is the right exponent. So if I do expected value of sensitivity of x to the power alpha, where alpha is less than half, then majority beats dictator. Then majority is better than dictator. So this kind of gives you the right exponent. So this kind of this probably is the right exponent to look at, or the tightest exponent to look at. Majority would beats dictator. So that's one thing. So that's motivation for that's a motivation for this conjecture, partly of motivation. So another thing, so let's see. So I'm going to tell you something more I know about this conjecture is the following. Oh, I can verify. So this has been verified for all Boolean functions with up to 8 variables. So you can verify those doubly exponential. You can restrict the class of functions just like they did. You can run. So this is true until at least 8 variables. Another thing is, so what is the conjecture saying? The conjecture is saying that square root of 1 minus EF squared minus square root 1 minus expected value EF of f given y squared is less than or equal to 1 minus root 1 minus rho squared. So one could imagine that if I don't condition all of y, but if I condition a Boolean function of y, so this would imply a following weaker conjecture, that is square root of 1 minus expected value of f squared minus expected value of square root of 1 minus expected value of f given some Boolean function of y. So I'm allowed to convey back only one bit. This squared would be less than or equal to 1 minus root 1 minus rho squared. So this is similar to asking whether this conjecture is true. So I f of xn g of yn. By data processing, if this is true, this must be true. Of course, this is achievable. So the question is whether you're weakening this to just a Boolean function. So g is also Boolean. So you're asking whether this is true. And again, if I prove this, this will imply ifg is less than or equal to 1 minus h of 1 minus rho over 2. Okay, so that's even the pair. Okay, now I'll tell you what we know about this. So what is the issue? The issue here is that we have xn yn, we have f of xn, and we have g of yn. So these are, say, let me call this u and v. These are binary variables. We want to somehow control the fact that they come from xn and yn. How do we control the fact that they are coming from xn and yn? So one thing I can say is that so clearly if I could the maximal correlation, so if I look at the correlation squared between u and v, this must be less than or equal to correlation squared between xn and yn, which is my noise parameter rho squared. So then you can ask whether so if I take any two random variables with correlation given by rho squared, is it true that this thing holds where u and v take values in plus minus 1? And that's not true. So it's not true that if I take random variables whose correlation is rho squared, whether this, so I'm trying to relax the problem into for just binary variables, and I am trying to impose some constraints induced by this on the UV, and what I am claiming, this is not good enough, not good enough, not good enough, that the rho squared is less than, I mean, it's less than or equal to this thing. But what is good enough? Okay, this is, it's not fully rigorous, it's numerically verified, and we have almost, I mean, this is 3 variable inequality. So what is verified is that S0 of UV is less than rho squared is sufficient. So what do I mean S0? S0 is the reverse hypercontractivity, at p equals 0. So if I, so S0 of x and yn, we know this is rho squared. So we know that this must be satisfied, and that's enough. If I take any random variable, any binary variable which satisfies S0 less than rho squared, then this must be true. Okay, so you can show that. So this is a good constraint. So hypercontractivity is a good constraint to impose on random variables based on this. And the last thing I want to say is that S0 to me is a dual of S star. It's something like a dual of S star, and that's something surprising, but that seems to be true. So this is mainly, so S star was something I discussed yesterday. So S0 and S star doesn't work. So I could put any SP, I could put any hypercontracted P, all of it rho squared. So the only one we have found that works is this S0. No forward hypercontractivity works, so only reverse works, and it's 0. So what is S0? S0, so what is S0? S0 has this, okay, what is S star? S star was the ratio Q over P as hyperconductivity has went to infinity. So this is also given by, so I fix a channel, so what do I do? So this is also a Gauch result. I fix a channel W and I compute the supremum over all input distributions nu x as different from the actual true input distribution. I compute the output divergences mu y over d nu x mu x. So I fix a channel and I take this maximum ratio, and that is my S star or S infinity. S infinity was this. So because channel is fixed, I could also write this as supremum nu x not equal to mu x, the optimal mu y over d nu xy because channel is fixed. So this is same as this. What is S0? S0 or 1 minus S0 is equal to infimum. So S0 is supremum, 1 minus S0 is infimum over all output distributions nu y of d nu y over mu y over another infimum over all channels. Now you fix the input distribution. So your infimum is over channels W1 such that when I apply W1 to my original mu x, I give the distribution nu y d nu xy mu xy. So here for S infinity I keep the channel fixed and I vary the input distribution. Here I keep the input distribution fixed and I vary the channel, and that's the reverse hypercontractivity. So it's the same expression, but I'm instead of varying the input distribution, I'm varying the channel. So there's some kind of duality happening here between channel and input, and that's S0, and somehow this is more powerful than S infinity, to at least in this context. S infinity doesn't work, but this works. And the proof of this is, if you look at yesterday's argument, that gives you the proof of why this is true. And this is the reverse hypercontractivity. So there is some very strange thing happening between the input channel duality. And yeah, so once you have this, you can plug in. That's how we plugged in for any binary with input. And in fact, there's a lower bound and so on, so that you can work from here. So that's this. So this is an application of hypercontractivity, and an application of hypercontractivity with by using the information measures we found out, and then we could show something. So without this, it would be hard to compute what is the right hypercontractive parameter. So that's basically what I wanted to. Yeah, I think my time's also up. So that's what I wanted to say. So yeah, if you want to know, I'll be here for 1 more week. So if you want to know any of this, I can tell you in details. I mean, there are some arguments here. There are some nice bounds here. Or if you want to know about the Gaussian thing, I can explain more detail. Or if you want to know what the thing I didn't tell about in either of the talks is what are the functions that I guess are subadditive, which solve big 40-year open problems. So there are some functions which I believe to be subadditive, and which I don't know how to show, or I mean various things. So I'm here for a week, so you can talk to me if you want, and that's all.